Well, in this video, I want to start talking about relations and functions. Functions, of course, being a special case of relations. So when I say relations, I mean a more specific thing than I meant in the foundations video. So a relation on a set will actually be viewed as a set. It will be viewed as a set of pairs of things in the set. So in order to talk about this, I need to be more precise by what I mean by pairs. I need to do a lot of building stuff. So the point of this video is to give a formal basis to a lot of the ideas which I expect people have already seen. So we need to know what a function is. We need to know what order is. We need to know what a binary relation is, and various other things. We need to know what set of pairs is, and so on. So all of these things require me to know what pairs are. So let's start with pairs. So from the axiom of pairing, I know that if x and y are sets, whoops, sorry, jumped again there. So if x and y are sets, then there is a set xy curly bracket which has just x and y as elements. But in many situations, this is very useful. But there's also situations in which we actually care about the order of the things in the set. So and the multiplicity as well. So this has the the property, which is sometimes inconvenient, which says that xy is equal to yx, and in fact xx is equal to just x in a set because these have the same elements. So we want to construct a new object which doesn't do this, so we can remember the order of stuff and whatnot. So how do I do this? Well, all I have is sets. I want to define this thing, so I want to define uh, this thing, this pair AB, such that AB equals CD if and only if A equals C and B equals D. So we're going to define a thing which does this. And we only have sets to work with, so we're going to define it using sets. The idea is we're going to take each of our things and tag it with another set which tells us which position it was in. So definition. Definition. So if A and B are sets, then we define the pair AB by, well, first it has to be a set because everything in math is a set except for like statements. So by AB is defined to be equal to the set which has the elements A tagged with the empty set. Remember, this is the set with no elements, which exists by the axiom of the empty set and is unique by the axiom of equality. And this other thing, B, which I'm going to tag as well, I'm going to tag B with the set containing the empty set. So the empty set is a set by the axiom of the empty set, and the set containing the empty set is a set by the axiom of pairing, applying the axiom of pairing to the empty set and itself. And then the set containing B in this set is a set by the axiom of pairing. This is also a set by the axiom of pairing, and so this is a set by the axiom of pairing. And I claim that this set has the property that you can tell what things are and what order they're in from how it was defined. So sort of here's a theorem. So AB equals CD if and only if A equals C and B equals D. And this is the property that we want in the definition. Okay, that's a proof. So we basically break it down into cases. So first, this is my first example of saying something obvious and not proving it properly, but I'll explain. It kind of is. So if A equals C and B equals D, then these are equal because if you replace them in the definition, I'm literally just saying the same thing for each of them. So first, I need to point out that this is implication is obvious. So if I substitute A with C and B with D in this definition, I get the same thing if I didn't do that and I have A and B being the same. Okay, so this is just defined in terms of A and B. So if I know what A and B are, I know what this is. Okay, so the other way around is less obvious. So if these are equal, I need to conclude that A equals C and B equals D. So suppose I know that AB equals CD, and I want to conclude from this that A equals C, and I also want to conclude that B equals D. Well, uh, first, I want to conclude the first part is the same. So we want to show first that A paired with the empty set, oops, is equal to C paired with the empty set. Okay, so if these sets are the same, they have the same elements. A paired with the empty set is an element of this. C paired with the empty set is an element of this. So the only way this could possibly fail is if they paired in the other way. So if C paired with the empty set was actually equal to this thing, and if A paired with the empty set was actually equal to this thing using D. So, if this is not true, then because these are both elements of this set, they have to be different elements. Then A empty set is equal to not this one, it's the other element of this set, which is D set containing empty set. And I know conversely that C empty set is equal to the set containing B and the set containing the empty set. Okay, and this is going to be sort of silly, so give me a sec to copy this. Okay, so now I know that these sets are the same, which means they have the same elements, which means first note C has to be an element of this set, and the empty set has to be an element of this set. So the empty set is not equal to the set containing the empty set, because the set containing the empty set has an element, which means this equality implies the empty set is equal to B. So B is empty. Okay, and similarly, this equality implies that D is empty. Okay, which means I know that C empty set is equal to, here I've got B, which is empty, and I've got the set containing the empty set. Okay, so this set contains the set containing the empty set, and the empty set is not equal to it, which means C is the set containing the empty set. And similarly, I know that A is equal to the set containing the empty set. Which means C equals A, which is what I wanted to show a second ago. So in this situation, I know that uh, C equals A, and in particular, these sets are equal. In fact, that's stronger than what I wanted. I showed that C equals A directly. So in this situation, I showed that C equals A if this is not true. Uh, and my assumption here was that these sets are not equal. So I have either C equals A or the set containing A empty set equals the set containing C an empty set, which also implies that C equals A, because A has to either be C or the empty set, which is fine if it's the empty set. But if A is the empty set, then this is the set containing the empty set, which means C is the empty set. So A equals C. In either case, A equals C. So A equals C in both cases. And I just concluded from the start that A equals C. If this is true, then A equals C, but the thing I just said about the empty set. If this is not true, I can conclude from this logic that A equals C. Okay, so here I got A equals C. So great, what's next? I want to show that B equals D. So I'm going to use similar logic. I'd be tempted to just hand wave this and say it follows by similar reasoning, but let's do it the same way, like in full detail. So yeah, first, if B set containing the empty set equals D set containing the empty set, then either B is equal to D, which in case we're done, or B is equal to the set containing the empty set, in which case this is the set containing the set containing the empty set. And so D is in there, and so D is equal to the same thing, and then D equals B. Then D equals B, or D equals the set containing the empty set, which is equal to B. So D equals B. Okay, so if this is not true, uh, if B paired with the set containing the empty set is not equal to D paired with the set containing the empty set, then it must be equal to the other element of the tuple. So B set containing the empty set is equal to D, is equal to the other thing, which is C, just the empty set. And D is also equal to the other one, so D set containing the empty set is equal to A with just the empty set. And we actually already considered this case. So in this case, we have this situation here. And in this situation, we immediately concluded that B and D were both empty. Because here, uh, B has to be one of these, and D has to be one of these. And uh, so in this situation, the empty set is not the set containing the empty set, so it's equal to B. And the empty set is not the set containing the empty set, so it's equal to D. And so B equals the empty set, which is equal to D. So in either situation, we have both B. We have B equals D. So I just concluded by case analysis that if I have this equality, I must have both of these. Either directly, because they just match the nice way, or they match the not nice way, in which case it's true anyway, because they're both equal to the same sets, either the set containing the empty set or just the empty set. So this box means I completed the proof. So we have a notion of a pair. I have a pair which tells me if things are equal in the right order. So we have pairs. I want to define relations out of pairs. So how do we define relations? Well, first I want to look at the set of pairs of things. So if x and y are sets, then we define their product. X times y to be the set of pairs where the first thing is an x and the second thing is an y. So this is the things x, y, such that x is in x and y is in y. Now, you might say, why is this a set? There's no axiom which says this is a set. But you can prove it using the other axioms. So if you look at these pairs here, this pair, it's a set of subsets of subsets of subsets of the set containing A, B, and the empty set. So note A paired with B, it's an element of the power set of A, B, union power set of the power set of A, B, union power set of the power set of the power set of A and B. And is that enough of them? Let's double check. So here it contains the empty set, which is in the power set of A and B. The set containing the empty set is in the power set of the power set. This is in the power set of the power set of the power set. And so I need one more power set. This is union power set of the power set of the power set of the power set of A and B. So this is a union of four sets, each of which was assumed to exist by the power set axioms and the pairing axioms. And so this is every element of every pair is in this set, And so this can be defined to be by the axiom of specification to be the things in this set which are equal to such pairs. So this is a set. It is well defined using the axioms. Okay, so given any two sets, I can look at their product. This is our Cartesian product. And a relation between two sets will be a nice subset of these. So a relation, let's make this a definition. A, oops. A relation between x and y is a subset of x times y. So it's a set of things which belong to the set. It's a set of pairs. Any definable subset is a set because of the axiom specification. You'll notice that I'm using the axiom specification a lot. It's a very useful axiom. Or axiom schema, I guess I should say. And we care about certain nice classes of relations. We care about functions and orders and various things. So I'm now in position to define a function for you, which means we'll finally know what the axiom of choice is talking about. Uh, so first note, the domain, we said the domain of the relation is this thing x, and the codomain is this thing y, and where x and y are inferred from context. So if R is a relation from a set x from a set y, then we call x the domain of R and y the codomain of R. So here I write dom R equals x, x and codom R equals y. And we'll often care about a relation which is defined on a single set. So it's a relation from the set to itself. In this case, we say it's a relation defined on the set. And here, the domain and the codomain will be the same. Okay, so definition. This is of functions. So we say that a relation from a set x to a set y is a function. R from x to y, so this is a subset of x times y, is a function if for all things in x, there is a unique y in y with x, y belonging to our relation. So y is the unique thing related to x by r. We denote y in this case by x r. It's like I'm applying the relation r to x, which makes sense because it only relates one thing to x, exactly one thing, because r is a function. Okay, so now the axiom of choice should make sense. Where C was our choice function. Okay, cool. We now have functions. The other relations I want to talk about in this video are orders and equivalence relations. Orders will be important because we need to talk about ordinals soon, because ordinals are required for cardinals to make sense, and cardinals are what give us our notion of size, in particular all our numbers, in which pretty much all of math is built on the premise that we can assign sizes to things and do sort of algebra to the numbers. So we're going to want to define cardinals, and to define cardinals, we're going to need ordinals. So we're going to need order. Before that, I want to talk about composition because function composition is important, and composition can be helpful when we're talking about the other properties of relations we care about. Okay, so uh, composition. So if I have a relation, or two relations, so if let's say, let's call them f and g. So if f from x to y, so this means it's a relation with domain x and codomain y. This is often, this notation is usually used for functions. It can also be used for relations. So it is a relation. And here it just means with domain x and codomain y. And I have another relation g from y to z is a relation. We define the composite f composed g. Note that some authors compose the functions the other way around, but this is the point is you're doing f first and then g. Some people would write this as a g composed f. So here I'm putting in my input on the left. If you're putting your input on the right, using left action, you're putting a function on the left, you would put like f on the right here. So the one I want to do first right now is f. So I'm inputting something on the left and then putting the function on the right. So this is defined to be the things. So this is a relation. It's a subset of x times z. It's a relation from x to z. So this is the things xz. Whoops. In x times z. So x times z is a well-defined set such that there exists something y in y with f relates x to y. So x, y is an f. Note that f might not be a function right now, so I can't write f of x. And y, z is in g. And g might also not be a function. If it's a function, then this is the usual notion. So this is a set, which is well defined because I'm using the axiom of specification here. And this is the definition of that set. It basically says you do this relation first, and then you do this one, and you relate everything that you can relate by going through these. Okay. And a useful thing that we want to talk about is that composition of relations is associative, which means it doesn't matter how I bracket it. So first notation, we often write just fg instead of f composed g. If the meaning is obvious from the context, which it often is. I want to start writing things like f, g, h, where these are all functions. This doesn't make sense yet because I haven't told you which order to do them in. It could mean like this or this. And what I want to tell you right now is that these are actually equal, so it doesn't matter which one you do. So now we want this. And this is called the associative property, so the bracketing doesn't matter. So I'll first prove that this makes sense. And it doesn't have to be functions, it's any binary relations. So a composition of binary relations is associative. So I really want to set up all the stuff I want to do with relations in this one video, which is why I'm doing this now. And once we've done this, we can actually start listing the other properties. Some of the properties can be nicely defined using these notions. So yeah, so proof. So I just need to check that these are equal. So suppose I have three binary operations. So I have f from x to y, g from y to z, and h from z to capital A are binary relations. We can just inspect what the definition of the composites are. Then f composed with g composed h. This is equal to f composed with, let's see, g goes from y a and y times a, such that there exists z and z with y, z, and g, and Z, A, and H. So this is the things, such that I can pair them with another thing. And then this composite is equal to the things XA and X times A, such that there exists a Y and Y, such that this is true, such that there exists Z and Z, such that XY, so this is the F bit, XY is in F, and I have that YA is in this composite, meaning there exists a Z such that uh, yes, so there exists a, I guess I should write it more clearly like this. So this is saying the first part, there exists a thing, so the first pair is in the first relation, and I want the next pair to be in the next relation. So I want Y A to be in G composed H, which is the thing above. In other words, this is equal to the things, because this condition here means YA and Y composed H means, it means precisely this thing, that there exists a Z in Z. We wrote it right here. It's just that YZ is in G and ZA is in H. So if we look at this condition here, we have there exists a Y and a Z. This is a Z such that XY is in F, YZ is in G, and ZA is in H. This is not sort of lopsided. It does not prioritize G and H over F and G. So if we think about the other composition, we will get exactly the same thing. Similarly, F composed G composed H. If we use exactly the same decomposition of definitions, we'll get the same thing here. And so these are the same thing. Basically, we can sort of follow the path through Y and Z to get from X to A. So they have the same elements. So F composed G composed H is equal to F composed G composed H. So composition of binary relations is associative. Okay. So now we've got that. The one last thing I want to talk about before we actually get to the properties is the inverse thing. So inverse of a relation if F from X to Y is a relation, then we define F inverse from Y to X by F inverse. It's the set of pairs whose reverse is in the XY. So this is the set of things YX and Y times X such that XY is in F. This is well defined using the axiom of specification. And okay. So then we have our things. I can start talking about the properties. So properties of relations on a single set. These are the ones which will give us our orders. Okay. And also our equivalence relations. So the first one is called being reflexive. So reflexive. So we say F subset of X times X is reflexive if for all X and X, I know that X is an F. In other words, it contains the equality relation. tablet is not being nice to me. 1 sec. Okay, we're back. So a relation is reflexive. I've lost the last thing I wrote, I guess. So yeah, properties. So reflexive. So f subset of x times x, so it's a relation on x, is reflexive. Reflexive if for all x in x, x, x is in f. It relates everything to itself. It contains the equality relation. So equality has this property. If you think of equality as the set of all pairs which are the same pair, and it's like all like the less than or equal to relation has this property, and all notions of equivalence have this property. This is an important property to have a lot of the time. So the next one I want to talk about being symmetric, which is why I defined inverse a second ago. So f subset of x times x is symmetric if f inverse equals f. So if every pair in f has its reverse also in f and vice versa. So this is what notions of equality have. If a equals b, then b equals a. And we just want to talk about things which have this notion of uh, reversibility. Yeah. So when we define equivalence relations, this will be more clear, and we'll have lots of examples of equivalence relations when we're building the number system. Basically, sometimes when we talk about things being the same in some sense, say maybe they have the same size or the same divisors or whatever, and we want to describe this as a notion of equality, and this will be a relation which relates things, and it will be the same both ways around. So if A is related to B, then B is related to A. That's what this says. This one is transitive. So this is the relation which says if A is related to B and B is related to C, then A is related to C. In other words, f subset of x times x is transitive. Transitive if f is a subset of f. Here I'm using composition of binary relations as I defined earlier. So this is saying if I have a and b in f and b and c in f, so a and b in here and bc in here, then ac is in f. We get this from the composite relation. So that we have this notion. It's useful to define these algebraically like this because we might do some algebra shenanigans to these relations at some point, particularly when we start talking about semigroups. Okay. So the next, these are the things I just defined are enough for equivalence relations, which we're going to talk about in a second. But there's a couple of things I want to talk about because I want to talk about orders. So the first thing, ordery, which is not equivalence relation E is anti-symmetry. So it's like being symmetric, but the other way around, like the opposite. So instead of saying that uh, the inverse of every pair is in there, it says if I have a pair and its inverse, then I have to have the same thing. So I never have both a thing and its inverse unless they're the same. So if x, y is an F and y, x is an F, then x equals y. Or equivalently, the contrapositive of this, uh, equivalently, x not equal to y implies, this is the implication symbol. So if this is true, then uh, we, we don't have x, y in F and y, x in F. I can't have a thing and it's backwards unless they happen to be the same thing. So if you think of this in the context of inequalities, so if A is less than or equal to B and B is less than or equal to A, then A equals B. This is what we want. And anti-symmetric, and it's symmetric, anti-symmetric. Okay. So now we have what we need to define what's called a partial order. So I want to take certain classes of these properties and give them names. So the equivalence relation will be the first three properties, reflexive, symmetric, and transitive. A preorder will be just reflexive and transitive. A partial order will be reflexive, anti-symmetric, and transitive. And the total order needs this other thing called being total. So totality. If x and y are an X, the set I'm working on, then either, we could have both, but either x, y is an F or y, x is an F. So we have to be related at least one way around. So if I have two numbers, for example, I know one of them is bigger than the other one, or they're the same. But if I have two sets, I don't know if one of them is a subset of the other, or vice versa. It could be that neither of them, each of them has an element that the other one doesn't. That's possible. So this would not be like a total order thing. And the last one I want to talk about is being well-founded. But to do this, I want to talk about sort of the other orders first, so it makes more sense. So important types of relation. So first, an equivalence relation. This is a relation which is both which is reflexive, symmetric, and transitive. So this is symmetric, reflexive, and transitive. The next one I want to talk about is a preorder. This gives the notion of being reflexive and transitive. So this is sort of a weaker thing than equivalence relation. We'll see later that you can use preorders to define equivalence relations. And in fact, you can use them to define partial orders after you've got your equivalence relation. And then a partial order. Partial order. This is reflexive, anti-symmetric, and transitive. So again, with subsets are a good example of this. If you have a collection of sets, the subset relation is a partial order because if two sets are contained in each other, they are equal. Every set is a subset of itself, and if A is a subset of B, then B is a subset of C. And the total order, this is reflexive, symmetric, transitive, and total. So this is a total partial order. So I have to be able to compare all things. And the last one I want to talk about is called a well order. So in the context of these orders, it's common to think of them in terms of ordering things. So we say less than to mean in the context of orders, we say A is less than or equal to B with respect to F. F is my total order. If A, B is an F, this is a common symbol for F. F is more like a function. So this notation you've probably seen before. So this means A, B is in this, and the context is usually this is an order of some type, perhaps a pre-order, a partial order, or a total order. We say this is less than this. Okay. To define well-foundedness or well order, there's lots of ways of doing it, but the way I want to do it is using the notion of minimal element or minimum element. Uh, so side point, we say that an element of a an ordered set. So a set with an order on it, a pre-order, total order, or partial order, is minimal if there is no smaller element. I.e. m is minimal if a less than or equal to m implies a equals m. And we say minimum if every element is bigger than it, bigger than or equal to it. If every element is greater than or equal to it, every element of the set on which the order is defined is greater than or equal to it, i.e. A is greater than or equal to m for all a. And here I'm doing this thing where we write the order backwards to write the inverse. So here, this thing here is defined to be this inverse. And I think of this as an order, like the inverse of an order. So this is the inverse of a partial order, or some sort of order. If I have this order in context, I'll often write this instead of like implicitly assuming that I'm talking about the inverse of this order, which is deduced from the context. So this is saying every element is bigger than m, bigger than or equal to m. And the last definition, we say that an order is a well order if every non-empty subset of the domain has a smallest element, has a minimal element, or minimum element, and the order is a total order. So I guess I should say that a total order has a minimum element, which in the context of a total order is the same as having a minimal element, but minimum element. So if we take any set of uh, any bounded below set of whole numbers, it will have this property. If we look at all the positive integers, this will be a well-ordered set, and we'll talk about that more later. And the ordinals will be important. They will classify all the well orders, and it turns out every set will be well orderable, and this will give us a good way of corresponding sets to each other. We'll sort of order them, and then we map them using their orders. Okay. So now that you know what the types of orders are, I've told you about equivalence relations. I want to point out why equivalence relations are important. And uh, yeah, so importance of equivalence relations. Their equivalence relations are important because they're equivalent to what we call partitions. Importance of equivalence relations. Okay, so if so first, what is a partition? So a partition in a way is breaking up a set into smaller sets. So we say that we say a set P contained in the power set of a set X is a partition of X. If every element of X is contained in exactly one element of P. If for all X in X there is a unique block, block being an element of a partition, there is a unique B in P such that X is in B. So we can say, we can break the set big X into bits, and these bits are called blocks of our partition. And equivalence relations, it turns out, are exactly the same as partitions in some sense. We can convert every equivalence relation into a partition, and we can convert every partition into equivalence relation, and these constructions undo each other. So, so here's my theorem, which describes that. So if X is a set, and this is sim, this is standard notation for an equivalence relation. So this is an equivalence relation. So it's reflexive, symmetric, and transitive. Equivalence relation on X. Then this set here, X twiddle for X in X is a partition of X, where what does this mean? This is the set of all these things. These things are called equivalence classes, where this means the things y in X such that X is related to y by this equivalence relation. And moreover, every partition can be arised in this way. So I should have said the partition is not allowed to contain the empty set as an element. I should have said that. So I'll write it like this. P is a subset of the partition, the power set of X without the empty set. So this notation means the set of all things in here which are not in here. So this is the set of non-empty subsets of X. So a partition is not allowed to have the empty set as an element, although I didn't say that earlier. My apologies. So, so this is an equivalence class of X. For the equivalence classes of the element of X partition X is the claim. And moreover, every partition is of this form. Okay, you might notice that this looks like it has lots of overlaps because you can take things which are related and you give them like, so X related to Y, then the equivalence class of X contains X and Y, and so does the equivalence class of Y. So it looks like these things are not disjoint. There might be a thing which is in multiple of them, but if it turns out if X is in the equivalence class of X and Y is in the equivalence class of Y, and Y is in the equivalence class of X, then the equivalence class of X is actually equal to the equivalence class of Y. So I do not have two different things in this set which have the same element because the things which have the same element are actually the same thing. We could prove this, but it's sort of just symbol pushing. Basically, if you have, you need to show that every element of X is in one of these. This is true because it's in its own equivalence class. Everything is related to itself because this is reflexive. If a thing is in two of these, then we can prove that they're actually the same set. We can show that all the elements uh, of one equivalence class are in the other equivalence class using the transitive rule and the symmetric rule. So basically, like these things will be either disjoints or the same, which is what the condition here says if you think about it. Yeah. I won't bother to write out the proof of that. Every partition can be arised in this way. If you have any partition, you can construct equivalence relation from it by saying two things are equivalent if they're in the same block. It's very easy to see that this is reflexive, symmetric, and transitive. And another side note, I want to talk about how to get from a preorder to a partial order, and then we'll end the relations video for now. So preorder to partial order. So remember, a preorder is symmetric and transitive. It's not necessarily reflexive. So it's reflexive and transitive. It's not necessarily symmetric, and it is not also not necessarily. It's also not necessarily anti-symmetric. So if it was symmetric, it would be an equivalence relation, and if it was anti-symmetric, it would be a partial order. And it turns out you can turn it into both an equivalence relation and a partial order, essentially. So if X is a set, and I have a preorder on X, and less than or equal to is a preorder on X, then I can define this thing, sim less than or equal to, an equivalence relation defined using this preorder. It's the set of things A, B in X such that A is less than B and B is less than A. This is obviously symmetric, and it is also reflexive, and you can check by thinking for a bit that it's also transitive, so you can prove very quickly that this is an equivalence relation. It's essentially transitive because less than or equal to was transitive. Okay, so this is an equivalence relation. We can take its equivalence classes. So this is always an equivalence relation, which we can get from a preorder. And I want to get a partial order out of this. This partial order will be defined on the quotient set. So we can define, we define the quotient of a set by an equivalence relation, which I write like this. So here's my equivalence relation, and here's my set, which I'm quotienting by. So this is the set of equivalence classes. This is the partition we get from the equivalence relation. X and X. And then we can define a partial order on this. We can then define a new thing, a relation, a partial order on the quotient thing. So we order the equivalence classes, the parts, by saying that one equivalence class is less than another one. If the elements are less than the elements. Because of the way this equivalence relation was defined, it turns out it doesn't matter which element I pick. And it's routine to check that this is a partial order. It's reflexive and transitive because the preorder was, and it's anti-symmetric because if A is less than B and B is less than A, then by the definition of the equivalence relation, their equivalence classes are the same. So we can check that this is a partial order. It is well defined. And it doesn't matter which one I take in each equivalence class. I could take a different representative for this equivalence class, and the same thing would follow essentially because of the way the equivalence relation is defined. I don't want to give you the details of that because I've already been talking for like 50 minutes. But yeah, hopefully now we have a decent idea of how relations work, and now we can start using relations when we talk about more complicated things like ordinals and other fun set theory stuff. And basically all areas of math use relations in some way, so it's good to have a good understanding of them. Okay, bye bye.